Welcome to Lecture 19. In Lecture 19, we're going to be doing your POGIL activity 9B. It's on page 102. And this will be substitution nucleophilic unimolecular. So we just finished SN2, so this is SN1. So let's start with Model 1, SN1. So our starting compound, at this point you should be able to classify that. I apologize for the dogs barking. These are my neighbor's dogs. Okay, so this is an intermediate carbocation. Hold on. All right, so here's our intermediate, and you see that's a carbocation. Carbocation, intermediate. And then we have another step, step 2. And here, this is a fast step, so I'm writing the word fast. Okay, and then we have a step 3. I'll put it here. You have it in your book, so. And this is the reaction mechanism, too. H plus. Okay, so SN1 is a 2-step mechanism. So let's answer questions 1A. Step 1 occurs, did you circle slow? Slow. Step 1. Step 2 occurs fast. 1B. What bond is broken in step 1? You see that the carbon, the bromine, is broken. So you could write CH3, 3. Okay, so that is the bond that's broken. Okay, what bond is formed in step 2? So in step 2, the bond that's formed is this oxygen-carbon bond from the CH3. Okay, so you can write CH3, oxygen, carbon, and then you can put your CH3 in brackets there. And that is the bonds formed. Okay, 1D. Label the nucleophile and the electrophile for each step. And you'll have to do this in the leaving group. Draw curved arrows to show the electron movement. This is what I will be asking you to do in your mechanisms for your open response. So here we have, this is our delta plus, this is our delta minus, so we can see the polarity. This makes this your electrophile. This makes your bromine your leaving group, so you can just write Lg. And then your nucleophile comes in step 2, okay? So this is your nucleophile, and it's methanol, and it has lone pairs. So this is your nucleophile. And you'll see that since it doesn't have a negative charge, it is a weak nucleophile. And then you have to draw your electron flow arrows. So in step 1, you should just draw a single arrow, electron flow arrow, okay? So here you have 1. Remember in SN2 we had 2 arrows, and that generates your carbocation. And then your next one will be step 2, where you have these electrons going to form your carbocation. So there's your 2 electron flow arrows. You have one in step 1, and then you have to show a step 2, and that will be also a single arrow from the nucleophile to the carbocation. Okay, 1E, deprotonation. That's the step 3. Okay, this is your deprotonation. What does it say? It involves the loss of the proton. So you're looking at this proton here, and this is why the oxygen has a positive charge. Part of the incoming group to return to the oxygen to a neutral charge. Okay? Draw curved arrows to illustrate this proton loss. And a lot of times it's nice to go ahead and have something to grab it because the protons are not going to leave unless there's some electrons there. So I would just draw your nucleophile, and that is that would be that mechanism right there for deprotonation. All right, so let's go to 2. The mechanism for an SN1 reaction occurs in 2 steps, as shown in Model 1. As a group, discuss why the first step is slow and the second step is fast. Okay, well, this is all getting you to understand that the rate of this reaction is proportional to your electrophile only. Okay, so the rate of the reaction has a higher activation energy for the formation of the intermediate. It's an intermediate, so that means it's a valley, the carbocation. Okay, so which step would be the rate determining step? It's going to be step 1 because that's your slowest step, highest activation energy. This is going to be an endothermic process. And you're going to see that when we do the energy diagrams. Which step would be the rate determining step? Step 1. How many reactants are involved in that rate determining step? Just the electrophile, so 1. Based on your answer, explain why SN1 is unimolecular. The rate of the reaction depends only on the concentration of your electrophile. Okay, so only on that electrophile. And that's your rate law. All right, so 1E, 2E, 2E. The rate equation for SN1, they give you the rate equation, and your groups discuss how the rate equation supports unimolecular reaction. You can just say the same thing we've been saying. Okay, let's go on to Model 2. Okay, Model 2 is going to talk about the carbocation intermediates. And this is very important. So in step 1, we form the carbocation. Notice we lost stereochemistry, folks. Okay, why did we lose that? Because this is an sp2. There's no dashes or wedges. This is flat. It's planar. Has an unhybridized p orbital above and below the plane of a piece of paper. Okay, so we have to form, step 1, when you do an SN1 reaction, you need to form the most stable carbocation. Okay, leaving group leaves to form the most stable carbocation. And that's what this is going to focus on. So let's go ahead and answer questions 3A. What is the hybridization of the carbon with a positive charge? So did you circle sp2? What is the shape of the carbocation? Did you write trigonal planar? How many valence electrons does a carbon with a positive charge have? 1, 2, 3, 4, 5, 6. The carbocation is, should you write electron deficient? It's less than 8, right? Carbocation is most likely to react with an electron that is electron rich. Okay, so that's where the nucleophile comes in to react with the carbocation. So something that's electron rich. 4A. Rank the following carbocations from the most stable to the least stable. Recall that the alkyl groups are electron donating. So the first one, let's go ahead and write these out. I will write these out. If we were in class, I'd put them on the board and I would say, work in your groups and classify each one of these carbocations. And then I would have your group come to the board and answer this question. So let's just pretend like we're in class right now and you're working with your group while I am putting these on your board. Okay, so let's classify these first. So this carbocation is bonded to how many carbons? 2, 1, 2. So that's secondary. This carbocation carbon is bonded to 1. This carbon cation is bonded to 3 carbons. This carbocation is bonded to none. So that's a methyl. Okay, so we've classified them, and we're supposed to rank them. So I told you this, and you need to know this. Benzylic and allylic. It's actually more stable than tertiary, secondary, primary, and methyl. And I've even told you that methyl and primary won't even form. Okay, these are your carbocation stability. So what's the most stable? Did you say that's number 1? And then secondary would be number 2, primary would be 3, and then methyl would be the least. 4B, what cation type would have the lowest energy? Lowest energy is the most stable, okay? So lowest energy is most stable. 4C, based on the answers to the above questions, determine the order reactivity of alkyl halides in an SN1 reaction. And basically that is what I was giving you here. So you want to basically write this down and know this. In the space below, draw a potential energy diagram that illustrates the entire two-step SN1 reaction. All right, so let's draw our reaction energy diagram. Energy goes up on the y-axis, reaction progress goes on the x-axis. Okay, we have a two-step with a valley. So this is our valley. You're going to have something that looks like this. And let's put in our starting material, which was this plus methanol. Okay, that's our starting material. And then our intermediate is the carbocation. Okay, so there's the intermediate, the valley. And then our product was the ether here. This is the ether functional group. All right, so our first transition state was the formation of the carbocation. This is the highest activation energy. So this is your rate determining step. The second activation energy is here, and that is not as high. Okay, that's also a transition state. You can see that between your starting material and your products, that's delta H, a reaction, that's going to be exothermic. And where you're going to have the more stable carbocation is going to show up in the valley. So if that's a tertiary this right here might be a secondary carbocation. So that's why the lower the activation energy for your carbocation. All right, so where are we at now? We are on 5. So question number 5A. Starting with the carbocation shown in Model 2, draw the product that's formed if a nucleophile attacks the top of the carbocation and determine whether it's R or S. Okay, so we're going to draw this, and I want you to draw your carbocation. Okay, so then basically the bromine leaves, and we lose our stereochemistry now. We have this unhybridized p orbital above and below, and then methanol is going to come in, and it's going to go to the top. And so this is if it goes to the top, and you'll get CH2, CH3, hydrogen. So I guess this would come at you, this would go back, and then this would come to the top. Okay, and then if we had it come to the bottom, your nucleophile came to the bottom, that would be CH2, CH3, OCH3 from the bottom, CH3, hydrogen. So if this works out, so if you look at your stereochemistry here, we have 1, 2, 3, 4 hydrogens in back, so that's R. Here we should have 1, 2, 3. That is S, but R because hydrogen's the other way. Here we have 1, 2, 3, R, but then hydrogen, you have to switch it, so that's S. So you see you get racemic because it can go from the top or the bottom, your nucleophile. So draw the product if your nucleophile attacks from the bottom. Determine whether it's R or S. Okay, I put S. What is the stereochemical relationship between the products? 50-50. That's racemic. Retention of configuration means the incoming group replace the leaving group on the same side. Which product shows retention of stereochemistry? So R and R. So the top side, which would be 5A. Inversion of configuration means the incoming group replaced the leaving group on the opposite side. Which product would show that? 5B. Okay, so this is inversion. This is retention. Once your group has reached agreement on the above questions, determine if the products from 5A and 5B would be formed in equal amounts. If not equal amounts, which product would be favored? Because this is flat and sp2, it would be equally formed because you're sp2 intermediate. Okay, on to Model 3. Model 3 is very important. I would put a little star there because we're going to be talking about rearrangements. And this is to form the most stable carbocation. Okay, so this is cation A. 1, 2, hydride shift. This is fast. Okay. Okay, so this is cation B. Anytime a carbocation intermediates form, rearrangements are possible and do occur. So 6A, label the cations A and B as primary, secondary, tertiary. Which one's more stable? Okay, so you look at your carbocation carbon and you say, how many carbons is this bonded to? 1, 2. That's a secondary carbocation. So we look at this carbocation and we see how many carbons is this carbon bonded to the carbocation, and we see that that's a tertiary. Which one's more stable? Tertiaries are more stable than secondary. So B would be more stable. In rearrangement of A to B, which bond is broken? Okay. So which bond is broken? So do you see it's this hydrogen-carbon bond that's broken? So it's the tertiary carbon-hydrogen bond that's broken. What bond is being formed? Okay, so over here it's being formed. It's the secondary carbon-hydrogen bond that's formed. The electron pair in the bond of the CH tertiary is migrating, moving to the secondary. Okay, so that's what this curved arrow is showing you. Those two electrons there are going here, and it's taking this hydrogen with it. That's a hydride shift. How is this not a proton shift? That's what we did in acid-base chemistry. Okay, so that's an acidic proton. And if you look at the proton, a proton has no electrons. Hydrogen, a neutral hydrogen, just has one single electron. So if it has two electrons, it has a negative charge. If you take the electron away, you have a positive charge. So this is a proton transfer. This is a hydride transfer. Okay, the "ide" means the negative charge. Once your group has reached consensus on the above questions, determine why the rearrangement from cation A to B is fast. Okay, anytime you're taking a molecular weight of 1, it's going to be fast, folks. It's faster than you can do that. All right, that's why proton shifts are fast. That's why hydride shifts are fast. Hydrogen basically has no mass. All right, so it will go to a lower, more stable energy, and it will happen very quick. Draw the carbocations formed from migration of HA and migration of HB. This is something I would have you do on the board. So let's do this. All right, so if we migrate HA, here's HA. So we're going to take those two electrons and we're going to put them on the carbocation here next door. Okay, so when you do this, you draw everything else the same. So you see HB is the same, this carbon, hydrogen is the same. This still has a CH3 and a CH3, but you're going to switch places. So HA goes here, carbocation goes there. And they just trade places. That's what you do there. All right. And then let's do the next one. If we migrate HB. So if we migrate HB, we're going to draw the carbons just the same. So I'm going to draw the framework. HA stays in its place. Now we switch places. So HB goes here, where the carbocation was, and then the carbocation goes where HB was. Now we want to classify this. So this carbon, the carbocation, that carbon is bonded to 1, 2, 3 carbons. So that's a tertiary carbocation. Okay, this carbocation's bonded to 1. That's a primary carbocation. And I always do this one. This one's a secondary carbocation. Identify all the carbocations, the initial cation as well, formed from the rearrangement. We just did that. Which hydrogen will most likely migrate? Did you say HA? Circle A. Explain. Well, you're going from a secondary carbocation to a primary. To a tertiary. Tertiaries are more stable than secondary. So it will happen. All right, let's work model 4. We're going to have to decide when we're given a reaction whether it's going to go SN1 reaction or SN2. Okay, so here we are on model 4. And we have to figure out whether we're going to have an SN1 versus an SN2 mechanism. Okay, the first one's an SN2. The next one is a Savolysis reaction, meaning that the nucleophile and the solvents are the same. Solvents are a lot of times written over the reaction arrow. All right, so what does 8A ask? For the reaction labeled SN2, the alkyl halide is what? So the first thing you want to do when you're deciding, always classify the alkyl halide. Okay, so this one, this carbon bonded to the leaving group is bonded to one other carbon, so that's a primary, and that's your SN2. Okay, so did you circle primary? What type of alkyl halide reacts fastest in an SN2 reaction? A primary is very fast. Okay, methyls are also fast. So are allylic and benzylic. That's one they do have in common. Okay, so these are fast because they have no steric hindrance. You got to get backside attack. And that's your rate determining step. Okay, the nucleophile for the SN2, right here. What did you notice? The nucleophile has a negative charge. Strong nucleophile. Okay, that's going to be important for an SN2 reaction. So strong. For SN2 reactions, the rate equals the alkyl halide and the nucleophile. So the concentration or the strength of the nucleophile is important. Yes, the strength is important. A stronger nucleophile will cause a faster reaction in the SN2. And it's all about speed. A compound can go SN1 if it doesn't have an SN2 first. All right, so the solvent is, remember we mentioned the solvent before? You would want something that's polar, and you want something that's aprotic. So it would be polar aprotic. So here you have ether. That is a polar, and it's aprotic. That's kind of like diethyl ether, is kind of like THF. Okay, those are polar because you have oxygens, and there's no hydrogen on the oxygen, so those are polar aprotic. How would this affect the strength of the nucleophile? It would increase the strength of the nucleophile because it would free up the CH3OH. I mean, you can imagine if you have a hydrogen there in a polar solvent like methanol, like what we have in the next reaction, that hydrogen there would bond to this negative charge and it would weaken the nucleophile. Okay, let's look at question number 9, 9A. The reaction labeled SN1. So now we're going to look at the SN1 reaction. The alkyl halide is a tertiary, right? So that is bonded to 3 carbons. So this is a tertiary alkyl halide. What type reacts the fastest? A tertiary reacts faster than secondary. But remember, allylic and benzylic also do react fast. The nucleophile this is your nucleophile. There's no charge. Still has lone pairs, so it's still a nucleophile. But this is a weak nucleophile. Okay, so we have a weak nucleophile. And for the SN1 reaction, the rate law is K times just the electrophile. So that's why you can have a weak nucleophile. The rate does not depend on the concentration of your nucleophile. It's only dependent on your electrophile. So what's the solvent here? Well, methanol is polar, and it has a hydrogen bonder there, so it's polar protic. Would the solvent be capable of hydrogen bonding with the leaving group? Yes, so that can stabilize the bromide a little bit, which would help the intermediate. What's the intermediate there? You always want to draw your intermediates for your SN1 reactions. Okay, the carbocation. Would the solvent be capable of stabilizing the cation intermediate through dipole interactions? Yes. How would these factors affect the stability of the intermediate? Well, it would stabilize the intermediate. And if it stabilizes the intermediate, it will have a faster reaction, because your reaction is dependent on the formation. Your rate is dependent on the formation of that carbocation. Okay, let's go to question number 10. Once your group has reached consensus on the above questions, predict whether an SN1 or SN2 reaction will occur in the conditions below. Complete the table providing an example of the reaction conditions which is capable. I am going to let you do this as part of your additional problems. So in your additional problems, I want you to include the table in question 10 on page 107, because I think that would be a good exercise for you to fill in. Do your reflection on this. This would be good to do reflection, and then your additional problems. Your additional problems, you're going to have to decide whether these are SN1 or SN2 reactions, and show stereochemistry. If your starting material shows stereochemistry like dashes and wedges, then odds are you're going to have to show it in your product if it's a stereochemical reaction. All right, good job.